Hi, this is Ms. Dahlberg. Welcome to AP Chemistry. Today we're talking about kinetics again, and we're in the second part of kinetics where we're talking about integrated rate laws and half-lives. And so if you look on your formula sheet, you will see that you have these three little formulas under kinetics, and we're going to talk about these three today. Okay, and so the first one we're gonna get to is called the first order integrated rate law. Now, last time we talked about rates, and we said rate equals concentration over time. We also talked about how rate can equal the rate constant K. K, let me go back. I lost my pen for some reason. And times the concentration of whatever the reactants are. In this case, we must, it looks like we only have one reactant, possibly. And there's some little exponent there. And we said we could only get that by doing an experiment. Well, if that exponent right there is a 1, then we have a first order reaction, first order rate law rather. And using calculus, you would integrate it, and we don't have to worry about that now, but that's how you get this equation. And this is your first equation under the kinetics section, where you have the natural log of the concentration at some point in time minus the natural log of the initial concentration, if that's at 0 seconds, so that's really just the initial concentration, equals negative kT. This equation is on your formula sheet. It does not, however, say it's the first order integrated rate law, but that's kind of easy to remember because it's the first one. Now, the reason they do that, if you take this equation that they give you and rearrange it, you can set this up in y equals mx plus b form. And when you do that, if you take your y-axis and you make it the natural log of the concentration, and you make your x-axis the time, you get a straight line. And so if we look at that, if we do that, here's our natural log of the concentration. Here is the time. The slope of that line is k. Now, it's actually the negative of k. So, but this graph will only be linear for a first order reaction. If it's a second order reaction or a 0 order reaction, you will not see a straight line. So they might not tell you have a first order reaction. They might show you this graph. You have to recognize that if you see this on the y-axis and it's linear, it's a first order reaction. Now, let me go back to that. So looking at this, well, let's go ahead and talk about that now. We'll get to second orders in just a second, but you do have to know these three graphs. So all of this, you have to do some calculations also with these equations, but you have to know these graphs. So if you have plain old concentration, or we can even write it like this, just whatever the molarity is, concentration versus time, and it's a straight line, then it's 0 order. If you have the natural log of the concentration, Ln, then it's a first order reaction. Now, what we haven't quite reached yet is second order reactions. For that, 1 over the concentration, 1 over the molarity, will give you a straight line. So you do have to know those, and that is something that will help you out with, you know, the rest of the question. Now, you might have to identify which order the reaction is to write the rate law. So you know if there's like one reactant and it has a graph that is natural log of concentration versus time, that's a straight line, then it's first order Na, and you can write the rate law. So we'll practice with that. Also, you know that if you have this graph and it's first order, then this first equation on your formula sheet is the first order rate law. Easy to remember because it's first. This equation on your formula sheet is the second order rate law. Okay, so now this last equation is derived from the first one. And if you take the first order rate law equation and you take the natural log of, say, 1 molar, you can put in numbers, minus the natural log of the concentration, and this is like 0.5, half of it. So we have half of it. Oh, sorry, I'm writing this backwards. This one is 0.5 and this one is 1. So you start out with 1 molar. Sometime later, you have half molar or 0.5 molar, and that equals kT. Well, if you add these two guys or subtract these two guys, you get negative 0.693. That equals negative kT. And you rearrange that, you get this equation. This is the half-life equation because we just cut the concentration in half. And this equation you're only going to use for first order reactions. So I'm just kind of showing you where that one came from. So on to applying what you just learned. So it says using the data provided, find the rate law. And so by finding the rate law, we're going to have rate equals K rate equals K times the concentration of, now I have only one reactant, so I can write my reactant. I don't know what goes here. So how am I going to figure out with what I have what goes there? Well, the thing that's going to help me out with that is this graph. I have a graph that's linear, and on this axis it's natural log. So that tells me whenever I see this that it's first order. So I'm going to come back up here and I'm going to erase this little question mark and I'm going to put a 1 here. You don't have to put the 1, it's understood. And I'm just going to emphasize that that is a first order reaction. Okay. Now, the second thing I need to do is find the rate constant. Now my rate constant is K. I don't know what K is. Now, to find the rate constant, I can do a couple of things. I can get data. If I'm given the rate and the concentration, I can just solve for K. So if I come over here to my data table, I have my concentrations at different times, but I do not have the rate. So what I need to do is I need to go to, and I'm just going to go through to the next slide. If we look at this, ooh, I jumped one too many pages. Okay. To do that, if I take this equation, I said it's a first order rate law, so I want to use my first order rate law equation, and I want to solve for K. Now, all you do is pick a certain amount of time that has passed between, 0 seconds is the easiest one, and some other time. So if you plug in your concentration at the time you pick. You do not have to pick this amount. But if we go back to our data table, so they're looking at the time passing here and the time passing here. So this is the concentration change from 0 seconds to 50 seconds. So if you come over here, plug that into your calculator. By the way, don't get lazy and just watch going through the slides. Plug it in your calculator. Make sure you can do this in your calculator. But this is K. Now, if you look at this, you not only need the number for K, you need the units. How do you get the units for K? This is kind of tricky because if you plug in molarity minus molarity, you might want to go back and look at the fact that this is a first order reaction. Go back to this original equation that you wrote. If rate is always molarity per second and A is always molarity, K, if you solve for K, you're going to have 1 over seconds to get this side to match that side. So in order for K to have the correct units, you're going to have 1 over seconds to have molarity over seconds on both sides. So that's probably the best way to figure out the units for the rate law for the rate constant. Okay, the last step in this problem was to find the concentration at 500 seconds. We want to know what's the concentration at 500 seconds. And that was one of those things that's just off the data table. Our data table goes to only 200 seconds. So we can use the information that we have here and our rate constant that we just calculated to find that. So if we go back to our same first order integrated rate law, and we're trying to find what is the concentration at some time at 500. I'm going to put a little 500 here. At 500 seconds, I know the concentration from the data table at 0 seconds, my initial concentration. And I know K. I just calculated K. And I know the time. The time is 500 seconds. So if you just rearrange this to solve for A. Now, when you do that, you move this natural log to the other side by adding the natural log to both sides. So we have the natural log on this side. We have negative KT on this side. And we have the natural log of A. Now, in this step, everything's done. You can even get a number instead of leaving it in this form. And I have the natural log of A equals this. Well, I need to solve for A, not the natural log of A. So in order to do that, if I take both sides and I raise them e to the natural log of A, e to the whatever power this is, whatever that number turns out to be, when you solve this, and I'm not sure if you're there in math class yet, you get just the concentration. On this side, you actually have to use E in your calculator and all of this. Put this in your calculator right now and make sure you can get this final answer. You're going to want to be lazy and not do it, and just take my word for it that it comes out to this answer. But go ahead and try it in your calculator. Make sure you can raise E to this power. Figure out, make sure you're working your parentheses. If you notice, these are multiplied. There's a plus sign here. So be careful about how you enter that in your calculator and make sure you get this number. Okay. Now, first order reactions have a very special property. They have a regular half-life. And what that means is if you start with a certain amount, like say you have 1 molar, and a certain time later you have 0.5 molar, and then a certain time later you have 0.25, and then 0.125. We're just cutting it in half each time. Each time we're dividing it by 1/2 again. We notice that the time interval for this half of it to react is the same every time. So if we want to cut this in half, it'll be the same amount of time as it was for the first time, the second time, the third time. So first order, if you see evidence in a data table, now they might not give you a graph like this, it might be a data table with times and concentrations. If you see evidence that there's a regular half-life, it's a first order reaction. That's another way to identify. So now you have 2 ways, a regular half-life and a graph that is the natural log of the concentration. If you have this kind of graph, then it's a first order. If you have a regular half-life, it's a first order reaction. So okay, this one seems to be missing the first part, so we will go ahead and move on. But what it is, okay, this one had a graph that went with it, and I'm not sure where that page, it must have accidentally got deleted. But anyway, if we look at this, in this, we'll do one like this in class together. To find K from one of those graphs, if you have the natural log, the concentration, versus time, and you want K, you can find the slope. And that's what that is here. You're just taking, if you had this graph, you're finding the rise over the run and taking that, and that slope is K. Now, if you know K, then you can take this equation, or you could rearrange it to the half-life equation at the bottom. And to find the half-life, you just have this. This is what we did earlier. You have half and you have 1, so this is going to work out to be 0.96 or 0.693, sorry, on the top, divided by the K that you found by finding the slope, and that will give you the half-life. And so something to know, half-life is definitely proportional to the rate constant. So if you look at that, if you have a really long half-life, you have a very small rate. And if your rate is small, like it takes a long time for it to react, K must be small. Because if we look at that rate law, rate equals K times whatever the concentration is. If this is really slow, this is going to be a really small number. K is going to be small. It's going to take a really long time, so it'll have a big half-life. The opposite is also true. If it's really fast, this is going to be a really high number, fast rate, really fast. K is going to be big. And if K is big, then it has a very short half-life. Won't take long. Now, which of the following has a greater, or which of the following has a shorter half-life? Okay, so you have two different processes going on. You have two different rate laws here. And so we have, these are both first order, so they both have regular half-lives. You come over here and you have a rate constant. So this one has a rate constant of 400 something. This one has a rate constant of about 300. And so this one has a much higher rate constant than this one, which means it has a much higher rate. So which one has the shortest half-life? So yeah, if it has a really high rate and a really large rate constant, then it's going to have a short half-life. The smaller one right here, the smaller one will have a larger half-life. Why? Because this has a smaller rate, it's going to take longer for half of the reactants to react. Okay, which brings us to second order integrated rate law. Now, second order integrated rate law is very much the same as first order integrated rate law, except now you have a second order reaction, so it's raised to the power of 2 for the rate. So we have two ways to do the rate: change in concentration over time, that stays the same, or you can have rate equals K times A to the power of 2. Now, the equation for second order integrated rate law is 1 over the concentration this time. So 1 over the concentration minus 1 over the starting concentration equals KT. So this is just the concentration at some point in time, T. This is the starting concentration. Now, we kind of went through, if you have this, let's go back. You can rearrange this also into this form by moving this to the other side, and you have set it up into y equals mx plus b form, where this is the y-axis and this is the x-axis. And if you graph that, 1 over the concentration versus the x-axis, time, you will get a graph. And the slope of that graph will be K. Okay. Now you should, like we said earlier, when you have this on this axis and you see a straight line, then it's a second order reaction. This is the only one that will have a straight line if it's second order. The other ones, if it's a second order reaction, if you have the other graphs, they'll be curves. So if we look at this, here we go. Find the rate law, find the rate constant. So to find the rate law, rate equals K times the concentration. Now we have one reactant. We have NO2. And we don't know what the order of the reaction is. We've got to figure that out. The thing that we have to figure that out are these two graphs down here. So if we come down to these graphs, we're looking for the one with a straight line. We're looking at the one with the straight line, what is on that axis? If we look for this, it's 1 over the concentration, which means it's a second order. So instead of a question mark right here, we have a 2. So there is our rate law. If you have to justify it, what do you say? Because the graph of 1 over the concentration is linear for second order reactions. That's all you would have to say if you had to justify your answer to A. So B, the rate constant. The rate constant. We're trying to find K. I don't know what K is. So if we're looking for K, how do we do that? Well, if I have rates, I could go to this table and plug in some experiment and find the rate constant. But I don't have the rates. I have times and I have concentrations. So what we want to do is use our second order integrated rate law. If we use our second order integrated rate law and solve for K, if we pick two different times, our starting time and some other point in time, and put those numbers in, divide by that time, you get the rate constant, sorry. And so what you don't easily get, though, is the units. So anytime you ever have to find this, the units are important. So if you look here, you have molarity in the denominator. Here, seconds is in the denominator. So they are really molarity in the denominator, seconds in the denominator. I would always go back and double check. Go back to this equation. If you go back to this equation, I know rate is always molarity per second. I need this side to equal that side. I know this squared is going to give me units of molarity squared. So now I need to do my rate for K. What is K? I don't know. So to make this equal that, I need my K to add in seconds. I don't have seconds anywhere. I also need to get rid of one of those molarities. So now I have 1 over seconds times molarity. So this molarity will cancel one of those, and I'll have the same units on both sides. So that's a way to double check yourself. Okay. So here we go. Data from an experiment. Examine the change in concentration for a second order process. Sketch a line that shows the approximate result that would be expected if the same experiment was repeated at a higher temperature. Okay, so if it's at a higher temperature, what would happen to the rate? If you heat it up, you speed it up, and the rate increases. Why? Particles are colliding, and they're colliding faster, so the reaction is a little bit faster. And so if you increase the rate, what does that do to K? So if we look at that, this line here is the slope, or we could find the slope from it. This line will help us determine K. The slope of that line equals K. So if the slope equals K and the rate goes up, if the rate goes up, what happens to K? If the rate increases, I know our rate equals K times AB raised to the second power if this is a second order reaction. So if the rate goes up, K must also go up. So if K gets bigger, what happens to the slope? The slope gets steeper. So if we look at that, the slope on that graph would get steeper. And so this would be the line for that reaction at a higher temperature. Okay. Just a couple of practice problems. Let's see. Here we go. The isomerization of cyclopropane to propylene is a first-order process with a half-life of 19 minutes. The time it takes for the partial pressure to decrease from 1 to 0.025 atmospheres is closest to. Okay, so this is one of those exercises in don't let the big words throw you. Talking about isomerization. Do we care? No, we don't care. Propane. We just know, all we have to know is this is some kind of reaction going on. We don't even care what kind of reaction. What we do care about is that it's a first order process. And if it's a first order, we know there's a regular half-life. And that half-life is 19 minutes. Okay, and so if it's 19 minutes, every 19 minutes, half of our reactants react. So if you start with 1 atmosphere, "19 minutes later, you have half an atmosphere. 19 minutes later, you have 0.25 atmospheres. Another 19 minutes later, you have 0.125, half again, atmospheres. So we have undergone 3 half-lives, and to find how long, add them all up. Add them all up. And so if you chose B, you are correct. Now this question showed up in 1994, and that was a medium difficulty question. I think this is pretty easy. I think a lot more than just 49% should have got this right. But I have a feeling they let these first words in that first part of the sentence throw them, because it really was a pretty simple problem if you didn't let the isomerization and cyclopropane throw you. Okay, here we go. Here's another one. Now, we don't have to study, or we are not going to be tested on nuclear chemistry, but nuclear decay, radioactive decay, is a first order reaction. It has a regular half-life. And so if we look at this one, the half-life is 10 minutes. What weight of element X was originally present in a sample if 40 grams is left after 60 minutes? Okay, so for this one, you're working backwards. So we have 60 minutes, which is, there's a 10-minute half-life. We have 6 half-lives. So if we work backwards, this is what we ended up with at the end. 60 minutes, actually we'll do the arrow, the 60 minutes before, or 10 minutes before rather, we had 80. 10 minutes before that, we had 160. 10 minutes before that, we had double that, or 320. 10 minutes before that, we had 640. So now we're down 1, 2, 3, 4. 10 minutes before that, we had 1280. And 10 minutes before that, we had how much? 1560. And so 2560. And so if we look at that, that one's pretty easy if you can break it down. And so some of these are really that easy. In fact, last year's kids had one extremely similar to one of these last 2 questions. So in 1989, only 20% of kids got this right. So which leads us to Kinetics 3, which we'll save for the next video. Y'all have a great day.